you have three things. The first one is the easiest one, gradient descent. What's this? This is Poyak heavy ball method. So what's the difference between gradient descent and Poyak heavy ball? You have the blue thing. So this is gradient descent, this is Poyak heavy ball. I just show you, if I put this 0.01 or 0.5, sometimes it works, sometimes it doesn't work. So actually this one have a problem, okay? And then it means what? Perform black, that means gradient descent. And then move the updated x means black, in the direction of the previous step. That means this. For how big? How big is this vector? Is this number, right? Beta is larger than 0, okay? So this is the norm, so this amount, so you need a number. The beta scale with the size. And also, if your variable converges, that means k minus 1 is 0. Then done, okay? No need to do other thing, okay? Then what? What's Nesterov accelerated gradient? You put this whole thing, okay, let me draw. So now, Nesterov accelerated gradient, in a sense, is this thing in green go inside. So very complicated long sentence. You have this part stay there, no change. Okay. You have the gradient descent, the structure of the gradient descent, no change. What has changed is this thing now is the extrapolated version. So it is move the not yet updated x, this one, in the direction of the previous step for this amount, so this one, then perform a gradient step on this shifted x, that means this one, then add the momentum back, the orange one. Yes. So this is the crazy thing. Don't ask me how he come up with it. And then what? This is the algorithm. So what I previously just showed you for the funny GD for method 2 is I just add the blue thing. So what I do, I need this. So what I'm going to do is, before I run step 4, I make a code to store xo as previous x. That's it. So this is Poyak heavy ball. But then there will be a problem. I need to know what's beta. Beta is you need to tune. And if beta is 0, you go back to GD. Okay, very simple, right? So here's the diagram. If the level set of the function is very nice, it's a sphere, then the geometry fits each other. You don't need acceleration. You stop it in one time, one step. But if your level set is elliptic, then it does not match the circle argument. So this is the reason why it will go to here, not here. So that's why it go to here. This is because of the geometry. Now if you add heavy ball, you see the blue and the red behave differently. The blue is a little bit closer than the red. What's the beta? The beta is 0.1. What happens if I make beta 3 times bigger? Then in the second step, it also have a bigger momentum, so it go to here, but it can overshoot. This one is another example. It overshoot too much, but it is, so that means what? That means at here, both the blue and red are the same point. This is iteration 1. Iteration 2, blue is here, red is here, red win. So it's not always blue win, red can win. Red is gradient descent. So that means sometimes you have this, and we just see this, right, in the code. So that means that this is due to your beta is wrong. Then there will be a naturally good question. How do we know beta? The answer is we don't know. Okay, so again, let me say this. This is nice f. So if f is nice, gradient descent does not need acceleration. If f is nice, gradient descent does not need acceleration. If f is nice, gradient descent does not need acceleration. This is so important, so I have to repeat it 3 times. The reason why you need acceleration is because f is not nice. What does it mean not nice? The geometry is bad. That's the idea. Yeah, okay? So do not blindly always just do acceleration. It does not make you look cool, okay? So this is the idea. So then what is the beta? Small beta and big beta give you different behavior. For example, this one, the beta is small, blue is good. Beta is too big, blue is not good, even worse. In the long run, basically the same as the red one, okay? How do you get this kind of figure? I just showed you the code, okay? Then what? This is another funny figure. What happens if I change a different beta? So red is gradient descent, and now I plot different curve. Now you see, I plot the axis, the grid line, different color, make it thicker, as actually what I said, okay? And then also make it latex, okay? And then legend with a name, okay? Anyway, then red is what? Red is gradient descent. What is blue? Blue is gradient descent with heavy ball momentum, but the beta is 0.2. If I start with black, 0.0001, very small, it makes it crazily much faster. And if I increase it a little bit, is the yellow, it's also faster. It's faster than the black one. Then I'm curious, can I make it better? Oh, if I make it to 0.1, it's not so good compared to the black and the yellow. And if I make it even bigger, then this is also not so good. That means actually beta have a range. Then the natural question is this smaller beta the better? The answer is no. And also, is it bigger the better HM? The answer is also no. Then the question will be, what is the best beta? This is then research. There's actually a range you can choose for beta. And Nesterov give you a formula even for that, okay? So here is the, now we touch Nesterov. What's Nesterov? These are the 4 expressions. Actually 3. So what's gradient descent? Gradient descent is, what's heavy ball? You add this thing. What's Nesterov? You put this thing into here, and now we have this, right? This comes from what? This. Here's the idea. You can always implement Nesterov like this, but the thing is this is very easy to have error. So it's better to split them into 2 lines. This is why I do it like this. And because of this, it turns out I make a mistake. It's on y, not on x. So y is updated using x. Okay, I swap the x, y. Okay, y is updated using x. And then what? X equal this, I need yo. Okay, so here I need yo. Okay, and then x is updated using y. And then y minus yo. Let me see. Y new, yo, beta. Yes. X. Okay. X. Okay. Yxx. So this is yxx. Okay. Now if I run it. Okay. Now see. Yes. When you see this kind of behavior, that means okay. And now you see suddenly, I just put a funny formula here. Oh my gosh. You see, this is hard to read. Okay. Log scale. The gap is 10,000. This is 200, right? Okay. Let me make it 500 or maybe 2,000. Okay. Let me open here. So this is 10 negative 4. This is 10 negative 8. This is 60. Yeah. Now you see why this is crazy. I do a simple trick. Suddenly this becomes crazy fast. You need to plot in log scale because here you can't see it. They are touching each other. And you need to, okay, now you see it. Okay, but the thing is, if I plot in linear scale, you don't know how big is this number. Actually, this number is 10 to negative 10. But this, you cannot show it, so that's why you need to log. This is the reason why you need log scale. This is because the behavior are too similar to each other, so you need a log scale. And if this is not even good enough, you subtract by a y-axis, you shift the axis. But now you see, it's crazy. So let me go back, not this funny formula. I will tell you why there's a funny formula like this later. Let's say put it 0.001, or 002, okay? Okay, you see, now I put it 0.002 doesn't work. Actually, we don't know what the heck is this. Now here's the first thing. Nestor come up with this crazy formula. If you implement this, it will work. But you see, what I'm doing is that I don't do this. I'm just going to do a funny formula, something like this. This also works, okay? Yes, this is much easier to remember. This is very complicated. Actually, this works even better. That means actually you don't need to guess. You have a formula. Then the question will be, why the heck this work? Okay, so this is the Nesterov accelerator. What I did is actually the same thing, but now I'm not doing this crazy thing. I'm just doing the k. And then what I do specifically is I have minus 1. Why? Because if k is 1, this term is 0. This means at iteration 1, I do not start the extrapolation. At iteration 1, I just run a gradient descent. Because when k is 1, this is 0, right? And this means in the first iteration, I let the gradient go down first. I don't want to start this because, you remember, you have this kind of thing. I don't want it to go up in the beginning. I just want to, okay, go down first. And this is good. Why? Because usually gradient descent, the first iteration, you go down the most. So this is the reason why. The general formula actually is this. But now I just do this. This is an easy version of this complicated thing. Remember, this is beta, which I have to guess. I don't know what's the value, but if I do this, k minus 1 divided by k plus 3, magically works. And then now we go to non-negatively square. So what's non-negatively square? Non-negatively square is basically now we have the red thing. What's the red thing? Last week is we have this without the red thing. So what we do? Well, we know why. We have this. This is what we have. Now I have the red thing, so I need to make sure the red is true. So I do this. So I call a y equal to gradient step and I project onto the c, if I know how to do that. So what is the idea? So this is an example. Suppose I want, this is my c. That means everything is larger than 0. Now I want to solve this. What's the new thing here? The new thing here is this one. There's no this thing previously. This is the new thing. So what's the thing? Okay, two-dimensional case. I have R2. What is the C? This region. Okay, this is non-negative orphan. That means this is the allowed region. Okay, then what? This is 0. And then this is very trivial. If your x is already here, what you do? You do nothing. If your x is here, you project to the closest point, this. If your x is here, you project to the closest point, this. If your x is negative, you project to the closest point. What's closest point? 0. Then this translates to max with 0. Okay, so basically it's max and x. This is the easiest projection. So that's why your projection onto set C is just max. So this thing, I just write this means max with 0. Okay, so this thing means I do a gradient step, then I take this thing max with 0. And that is project the gradient descent. For this easy case, okay, then you replace this line in the update step. So let me go back to this. So now suppose what? This is the code, right? Now suppose I have such that x has to be larger than 0. Okay, now this is the code. What's new? Nothing new. No change, no change, no change. I change here. So this is x. I do gradient descent. Now I need to make sure it's not negative. So I just max it with 0. Done. This is the step that updated the variable, right? Look here, I have natural acceleration. I don't care. This is the step that have updated, right? Let's see. Go down. So now this is our example. So I have 50, 50, 50, 50, 50. Okay, let me do this. 50, 60. Okay, let me do it 50, 50. Okay, so now I have something like this. Okay, now I go out here. So now I have what? Projected gradient descent, I call it PGD. And I have a Nesterov accelerated gradient descent, I put an A here. A means accelerated. So constant T, that means 1 over L. Exact T, that means the exact step size. Very slow. And if I add Nesterov acceleration on top of this, but using this crazy formula, not the K thing, but this crazy formula, I have this. This is for 50 iteration, this is for 200. That means this part, I zoom in, I get this. And then this whole thing is, this part is this figure. Okay? Then now you see, in terms of log scale, wow, you look at here. This is 10 to negative 10. This is 10 to negative 200. Okay? This case is a special case because B is 0. So you see, PGD is monotonic. What's monotonic? You always have Fk plus 1, what? Smaller than Fk. This is always true. But Nesterov, you can go up. The idea is, you allow, in some iteration, go up, but in the general global situation, the whole curve is much faster than you need this. So this looks good, but actually it's limiting the whole thing. This is why sometimes you allow something to go up a little bit. This also can think of as like escaping local minima, but this is not correct here. Because here we have convex problem. Convex problem, no such thing called local minima. Okay? Local minima are global minima. And also if my problem is strongly convex, there's only one global minima. So you don't have so-called escape from local minima. You always are going to the what? To the global minima. So this idea. And then what? Why you have this? This is the same idea as this vector. At this step, I go too much, I push too much, so I get worse than the red. This is the idea. You push too much, but in the end, you go back to here much faster than the red. So let's look at this vector. So this is starting point, so step 0. Step 1, red go to here, but blue already here. Blue win. Step 2, red go to here. This circle, the cost value is about 0.5. Blue go to here, the cost value is 1, so blue lose. So both red are here. So let me use color. Red are here. Step 1, go to here. Step 1, blue go to here. Okay? And then step 2, red go to here. So red go to here. Blue go too much. So actually what? Blue even grow bigger. So this circle is 0.5. This circle is 1. So blue actually have this. Okay? Step 3, blue go to here. Okay? This is almost 0.5. So go back to a little bit before. What's red? Red go to here. This is let's say 0.25. So red keep going down. But then in step 4, blue suddenly jump to very close to the cross. So in step 4, like 90 degrees. But the red is still. So that's why blue is winning. So if I draw this in a bigger picture, it is this kind of thing. You can have going up. So it's called monotone. Number 2, of course, is faster. But how do you tell it's faster? You tell faster by this angle. Okay? And this angle. You can see they are different slope. Okay, suppose I have a sequence. AK. Okay, I have AK. It is something like 0.9k. Okay? And then I have a BK. Okay? This is what? 0.5k. They both go down to 0. But if you plot linear scale, you get this. How do you see which one is faster? You plot a log scale, then you have put a log here. Then you have k. This also have k. This one you have log 0.9, which is some number. This one you have log 0.5, which is some number. Right? Both are negative because they're smaller than 1. So this one give you what? Give you a negative slope. I call it C1k, which is a slope. And then this one give you a C2k, which is also a slope. Then of course they have different straight line. One is like this and one is like this. So that's why you see this. Because they behave like this. This is actually 1 over k. So it's what? Negative 1. This is actually negative 2. So this is 1 over k squared. Of course it's much faster. Good. Okay. Then this is madness. This is what Nesterov proposed. Later he proposed this. This is another one. This is actually called Fish-star. And then the formula I just gave you is coming from Paul Sang. And then if your function is what? Strongly convex and L smooth, you actually have an even better number called conditional number like this. So the largest eigenvalue divided by the smallest eigenvalue is the conditional number. This is from linear algebra. And then you take this inverse. I call it kappa prime. And then put like this. This is also a beta. This actually is the best one. Yes, but you need to compute eigenvalue problem. Okay, so you have 1, 2, 3, 4, 5. Okay, these are madness. This is easy. This is also okay. Yeah. So these are the behavior. So this is non-negatively squared, 100 times 100 matrix. This is gradient descent, constant t. These three are what? Nestor parameter, Poisson parameter, or conditional number. More or less the same. Well, they are different, but if you look at the slope, more or less they are the same slope. If they are the same, of course we do this one. Okay? Easy. Okay? Okay, this one tomorrow.